Good morning and welcome. We're very happy to have you here. My name is Louis Morel. I'm a member of the Science, Medicine, and Technology group, and our team is very happy to bring you this presentation today. If you haven't done it already, please silence your mobile devices. They're very distracting for the speaker and for the other members of the audience as well. Thank you. Also, welcome to the people joining us online via cyberspace. And special thanks to our course technician this morning, Amy Weber, for supporting this hybrid presentation. If you have any questions or comments during the presentation, raise your hand. I will bring the microphone to you, and then everyone, including those in cyberspace, can hear you. If you're a veteran or interested in learning about a special part of military history, HASP is proud to celebrate Veterans Day with a program introducing challenge coins. This program invites you to bring your own challenge coin collections, share stories, or learn about the origins, design, and camaraderie of these pieces of history. You can join us in this room, the HASP classroom, next Monday, November 13, at 3 p.m. for this program. Let me tell you about our speaker today, Frank Roldán. His interest in astronomy started when he was in elementary school. It was the result of a field trip to a planetarium. He was hooked. From that moment on, he read as many textbooks on the subject as he could, and he added an extra dimension to his new interest, building telescopes. He's been a member of various astronomical associations during his lifetime. For several years, he was the chairman of the North Central region of the Astronomical League. He's participated in a number of research programs providing data to professional astronomers. Just this past summer, Frank taught at the Kennedy Space Center, and I hope that later on he will be able to share with us what his role was. Our speaker has been a member of the Shoreline Amateur Astronomical Association since 2007. The group has its base at Hemlock Crossing, and currently Frank is the observatory director. One more note on astronomy. For those of you who are interested in photographing the heavens, or those of you who may be inspired to do so after today's presentation, the first of two, Mike Shaw published a book last August. It's titled The Beginner's Guide to Astrophotography, and there's a copy available at Herrick Library if you're so inclined. Frank retired after a 38-year career in the telecommunications industry. He held many roles, starting as a technician, becoming an engineer, a district manager, and then, a general manager, and then a district manager. And as Veterans Day approaches, it's appropriate to highlight the fact that Frank served in the U.S. Army during the Vietnam conflict and is currently a lieutenant colonel in the Civil Air Patrol, the auxiliary of the U.S. Air Force. So without further ado, please join me in welcoming our speaker, Frank Roldán.
Oh, can you hear me okay? All right, well, good morning, everybody, and thank you so much for coming out on this crummy morning. Although if you've been living in Michigan for some time, then this is common things, right? So you can realize at this time of the year, I get a lot of phone calls. I want to buy a telescope for my son or daughter for Christmas. What should I get? Well, that's the $64,000 question. You guys understand when I say that $64,000 question, you know exactly what I mean. When I talk to youth, I gotta I gotta come up with a different term. So today we're going to be talking basically about telescopes. Try to understand what they're all about, how they work, so on and so forth. Okay. As I always say, we all have at one time or another used a telescope or a pair of binoculars, right? To look at things far away, nearby, etc. But exactly how they work. Light gathering, that's what the primary function of the telescope or binoculars is that to gather light, as much light as you possibly can. Let's say this morning, I had those two pans, one bigger than the other one, and before it started raining, I put them out in my backyard. So by this afternoon, whenever I get home, which one do you think will have more water in it? The bigger one, right? The bigger pan will have the most water in it. And why? Because it's got the bigger area, right? The area of a circle, let's go back to high school geometry. If you still remember, anybody remember the formula? Oh my goodness, I'm talking to academics here, so I should have known better than that. So to calculate the area of a circle, we definitely have a very simple formula where the area is equal to pi radius square. Okay. I'm going to give you a couple of examples. I have a circle of with a 3-inch radius and another one with a 5-inch radius. Right? If I apply this wonderful little formula, I will get the result that in circle A, the area is a little bit over 28 inches, square inches, that is, while in B is 78.5, right? Square inches. It's amazing how that fairly small change or increase in radius, of course, will develop into a quite large change in area, right? The area roughly has tripled here by increasing a couple of more inches to the radius. And that is why we see these gigantic telescopes that we keep building. Because the bigger the mirror or lens, the more light you're going to collect. And the more light we collect, the more we can see. Now, okay, so now once our telescope has collected or has all this light going into it, how do we handle that light? Well, let's go back to the old pan. So if I have this pan full of water and I go ahead and take a big funnel and I fit it right underneath it, and I can cut the bottom of the pan out, all the water, of course, is going to go into the funnel and come out at the very narrow end of that funnel. Well, I'll have a lot of water at that point because I have brought all the water to that point. Okay. The same thing as what the optical element of the telescope is doing. The shape of the lens or the mirror, we're going to talk about both types of telescope. Basically, there are two types of telescope. Where there is a lens or a mirror, they're shaped in a certain way in order to do that. To concentrate or bring all the light to one single point. Diagram of a convex lens, actually we call it a double convex because both surfaces are convex. As the light goes through the medium of the lens, the shape, the curve starts, I say bending the light is more like redirecting the light. And all the light rays that go through the lens are going to be brought to one point, somewhere behind it. Something we call the focal point. At that point, you're going to have a tiny image or whatever you're looking at, but it's going to be bright because you have concentrated all the light that came into the telescope into this one single point. Focal length, by the way, what you see there in the bottom is the term that we use for what is the distance between the center of my lens and where this focal point is. That's all that focal length means. In the case of telescopes, I use mirrors, and well, I'll be talking a lot about that next week when we actually get into the history and development of telescope. But some telescopes use mirrors, okay? And again, it's the shape, it's the curve that we grind into this mirror blank, which in this case happens to be a parabola. You guys remember what was kind of special about parabolas, going back to high school geometry? Well, in the case of a parabolic mirror, any light that falls on it will be reflected to one single point somewhere in front of the mirror. And that again would be the focal point. And the distance between the focal point and the center of the mirror, again, is what we refer to as focal length. Focal length, I'll mention that a couple of times because it's going to be becoming apparent as to why it's important. In the case of telescopes that use lenses, we call that a refracting telescope because we are refracting the light as it goes through the lens. In the case of a reflecting telescope, because the light is being reflected, that's where we get the term from. By the way, Newton is the one that gets the credit. I shouldn't say that now because that'll be part of next week of inventing the actually coming with the idea for reflecting telescopes. Now I mentioned parabola. That mirror is parabolic in shape. And parabola, to be honest with you, is something that is very common in our lives. You probably may not be aware of it, but you got them all around you. Everybody here owns at least one parabola, probably more than one. What about the headlights of your car? If you look at the headlight of your car, you'll see there's a reflective surface inside. And the shape of that metallic reflector, usually, well, today's are plastic, is a parabola. In the old cars, they were pretty simple, easy to see the whole thing. Nowadays, we have such sophisticated light fixtures in our cars, which, by the way, they're rather expensive. If you break one, you know how much it's going to cost to replace it. But we have parabolas. The light that comes from the bulb gets reflected by the parabola, and it gets actually, again, form into a beam of light in order to illuminate the road ahead of you. What about these things? What about flashlights? Again, when you go home, look at the front end of your flashlight, you'll discover that there is a parabolic reflector built in there. And once again, depending on the design of that particular parabola, will determine, are you going to have one nice solid beam or you have a much wider beam of light? Again, what is the flashlight going to be used for? What are you trying to illuminate? There are some flashlights nowadays that you can actually change the width of the beam by turning a knob or so forth. Kind of a multi-purpose flashlight. And what about these things? Anybody has one of those on the roof of your house? Well, it is an antenna and a receiver for television being broadcasted from a satellite. Okay. The shape of the dish, needless to say, is a parabola. This metal arm with this little box at the end, in the industry, we call that a snorkel because it looks like a snorkel from snorkeling. But right here, you have a receiver. And again, when the very weak signals come and hit the mirror, it gets all reflected to that point. From this point, there's a cable that goes into your home, right? And somewhere nearby your TV set, you have a box, and that box does a couple of things. It amplifies the weak signal that came from the satellite, and it gives you the ability to choose whatever channel you want to watch, as long as you have paid a subscription for it. So parabolas are all around us. There's many, many uses of them. So let's take a look at a refracting telescope and some of the main parts of it. Number one is the objective. That is the name that we use to describe the main optical element of a telescope, whether it is a lens or a mirror. We always call it the objective. And if you decide that you're going to go online and look through a catalog and you start reading about this telescope you're thinking of buying, you're probably going to come all kinds of terms that you go, what the heck are they talking about? Okay. So if you see the word objective, now you know what they're talking about. It's the primary optical element in the telescope. The second item is a tube. You need a good rigid tube in which to mount all these different components so everything is properly aligned and you can look through it. The focal point, remember, we talk about focal point. There it is, somewhere inside the tube. The eyepiece. The eyepiece is nothing more than a very sophisticated magnifier. Okay. Back in my days as a youth, they were rather simple ones, but nowadays we have some very complex eyepieces that can deliver an extraordinary image of whatever you're looking at. I think it has to do with having computer engineering or design work with computers, and you can do trial and error in the computer without building anything. Okay, and then the machines that we have nowadays that are computer controlled, that can grind mirrors perfect time after time after time after time. In the old days, we did everything by hand, and maybe out of 10, 7 were good enough, and 3 of them they threw away. So that controlled why the price of optics were so high years and years ago. Okay. But anyhow, the eyepiece again is a magnifier. It's going to take the little image and it's going to magnify so you can see detail. Needless to say, those fancy, beautiful, wonderful eyepieces that we can buy nowadays sometimes cost as much as the telescope itself. Let's look at, I'm not really going to talk a lot about binoculars, but just 2 things. What are binoculars? Well, it's nothing more than 2 telescopes strapped together. And the early ones, that's what they were. They were very simple, very straightforward. Nowadays, we can adjust the distance between the 2 scopes because the distance between our eyes differs from one person to another. We can focus different, the eyepiece is different because again, not all our eyes are all 20/20, you know. So they can do a lot of things with binoculars nowadays that we couldn't years and years ago. Some of them have even built-in gyroscopes to steady the instrument while you're looking through it. You know, I don't know if you ever looked through a pair of binoculars, but after a while, if they're heavy, you get tired and, you know, everything is moving and you need a tripod or something to support the binoculars. But these new ones now have a built-in gyroscope and they kind of self-stabilizing binoculars. Reflecting telescope. Again, let's talk about the different parts. Of course, the tube. Most of the time, most reflectors, the front end of the tube is open. There's nothing there. A couple of people experimenting with trying to put an optical window on it, pros and cons, but most of them are open in the front. Okay. 2, again, here's the objective. In this case, a parabolic mirror. The secondary mirror is this flat little mirror here. You have to realize that if the light comes in here, here's the primary mirror and it's centered right back to the front. Without the mirror there, the focal point will be somewhere close to the front end. So what are you going to do? You're going to stand in front of your telescope and try to look? Well, your head is blocking the light, so it's not going to work. So instead, oops, my apologies, press the wrong button. Instead, we have this little secondary flat mirror at a 45-degree angle that will intercept that cone of light and send it off to the side, on the hole in the side of the tube where the eyepiece is located. Do I lose a little bit of light because of the secondary mirror? Yes, I do, a little bit, but I can afford that when I have a large instrument. Yes, sir.
Frank, could
Yes,
you
sir.
repeat the question for the people online, please?
Oh, does the focal point have to be inside the instrument?
Well, does it have to be, it's right here, it's 1 flat.
No, the secondary, absolutely. It has to be beyond that. Yeah, yeah, right. Where it is varies a lot depending on optical design of the mirror and so forth. But yes, it has to be beyond the secondary. Okay. By the way, making a flat mirror, I mean, a really, really flat mirror is hard. It's very hard to make. Your bathroom mirror is, you know, in your bathroom or any mirror in your house, that glass looks flat, but it really is not flat. I mean, this one has to be super flat. Okay. Something about mirrors. Where is the reflective surface in your mirror, in your home? I don't care which one it is, bathroom or your bedroom. It's in the back, right? The reflective surface gets deposited in the back, which protects the reflective surface for one thing. What do you think about a telescope mirror? Where do we put the reflective surface? It has to be in the front. Why? Because if we put it in the back here, that light then has to go through the glass to get hit the reflecting surface and go back to the glass again to get out. And now the focal point is going to be nowhere. The light rays are no longer convention at one point. They get bent, they get moved, they get the direction gets changed, right? So it has to be a front surface mirror. The reflective surface has to be in the front. We do put some protective coatings on it when they're made to protect, again, the reflective surface, but everything, both the primary and the secondary, have to be front surface mirrors. It's interesting about the reflective surfaces in telescope mirrors. What do you think they use for the Webb telescope, the one that is the latest telescope out in space? What material do you think they use for the reflective surface? Gold. What do you think they use in my telescope? It's not gold. No, in most, I would say small to medium size to getting into the big size scopes is aluminum. Once the mirror is polished, and we'll talk about that next week. Once you're all done grinding and polishing the glass, and then it has to be perfectly clean. I mean, perfectly clean. It gets placed inside a vacuum chamber. Inside that chamber, there are electric heaters, and they take very thin strips of pure aluminum, put them by the heaters. When they evacuate the chamber and they turn the power on, and it happens fairly fast, those thin strips of aluminum vaporize. Now you have a chamber full of aluminum vapor or aluminum gas. And in a vacuum, those of you who are physicists, things get attracted to each other. And the aluminum gets attracted and deposited on the surface of the mirror, as well as the chamber itself. And that's how the aluminizing process is done. I will tell you that at big observatories, they have their own devices to do that system. Every so often, because if they're exposed to the elements, the surface will have to be redone. So that means they got to strip everything that's on the mirror, clean it up perfectly, and then redeposit a new reflective surface. So you can imagine, let's say, well, Palomar, that used to be the biggest scope in the world for a while back. You don't want to be carrying the mirror down that mountain to some lab to have it done. So they have all their own equipment right at the observatory. They simply drop the mirror from the telescope and put it into the chamber, and they clean it and luminize it and then put it back. Yes, sir.
Frank, tell us a bit more about this process of the aluminum strips. How much is left to randomness, and how thick is that layer of aluminum on the lens when it's actually adhering to it?
We're talking about thousandths of an inch. I mean, microns. Okay, it's not very thick. And like I said, by the time all the aluminum is vaporized, it pretty much will adhere itself to everything inside the chamber. So after a while, there's now nothing left in the chamber. Okay, everything has stuck to something, including the mirror itself. Yeah. Okay, get the mic. Yeah.
Thank you, Chris.
Why isn't that then rust? Why the aluminum surely is, it immediately dulls. It gets a surface on it.
Yeah, just to get the surface on it, I reflect the surface. We need to reflect the surface on that.
No, but isn't that surface then going to get very dull immediately?
No, you'll be surprised. It doesn't. It just comes out nice and shiny, just like when they aluminize, they use different materials. Your mirror for your bath.
Okay.
Yeah. They produce a little bit of light washing or something, but no, it's once it's there, it's very reflective, and you want to keep your fingers out of it. And by the way, if you have any optics, you have a little bit of dust on it, leave it alone, okay? Cleaning a mirror or a lens is something that needs to be done by somebody who knows what they're doing, because you can very easily scratch the lens or the mirror. A lot of the coatings that are placed, anti-reflective coatings that a lot of the optics have nowadays are delicate, you know. So you don't want to damage that either. And you definitely don't ever touch it with your bare hand. You don't want to leave your fingerprint, that grease, that oil that we have in our skin on the surface of the mirror or lens. So yeah, little dust, that's okay. Eventually, yeah, I may have to clean it, and then at that point, I go through the whole routine of cleaning it. But don't let just a little bit of dust say, "Oh, we got to clean this thing up." Yeah. Okay. So just a quick review. The objective, again, is whatever the primary optical element in your telescope is, whether it's a lens or a mirror. By the way, some telescopes use a combination of both lenses and mirrors, okay? There are many different variations of reflecting telescope. Not quite as many on a refracting telescope, but there's still some. So talk about reflecting telescopes. We see more, you know, right? If you watch the news, we keep building bigger and bigger reflecting telescopes, don't we? You don't hear about refracting telescopes being built. And there's a good reason for that. How do you support a lens? Those of you who are wearing glasses know how they're being supported. They're supported by the frame. They can only support them around the perimeter, right? Well, as you start getting bigger and bigger, you start running into a problem. Lenses for telescopes are fairly thin, okay? And after a point, they start getting heavy. And they will sort of collapse or deflect on their own weight when you try to support them only by the edges. Okay? And I'll tell you about the biggest refracting telescope next week. Nobody has been able to build one bigger than that to date, or want to be honest with you. Here's a photo of a lens in a cell, in a metallic cell. There's a refracting telescope. You can see the primary lens in the front. And here's a mirror blank and kind of a home-built type telescope that have become quite common and famous with amateur telescope makers. Aperture, okay. You may hear that and say, what do they mean by that? That refers to the diameter of your optical element, whether it is a lens or a mirror. To give you an example, here is a mirror blank. It hasn't been ground or polished or anything, but you measure across the diameter, and that is the size. That's the aperture. So if I tell you I have a reflecting telescope, a 10-inch reflecting telescope, it doesn't say that the telescope is 10 inches. It's talking about the diameter of the mirror in my telescope. I got a 10, I got a 12, I got a 26, you know, whatever. Focal point, we already talked about that. It's the place where all the light is gathered at and a small image is formed. Same thing, we talked about the focal length. It's the distance from the center of your optical element to where this focal point is at. It does play an important role in certain things. Just to, again, reaffirm it, there you have a diagram of a mirror and the light coming into, hitting the mirror surface, being reflected to the focal point. Comes here, hits the mirror, gets reflected, and all those light rays that come in perpendicular to that particular point in the mirror will get reflected to there, where the little image is formed. Focal ratio. Since with the word ratio, you should right away tell you this has to do with math. Yeah. And all it is, let me give you an example. Let's say that this is the light cone produced by a lens. So therefore, the focal length is the distance from the lens to where the image is formed. And let's say that the focal length of this particular lens is 200 inches. Let's say that this particular lens happens to have an aperture of 10 inches. It's 10 inches in diameter. Right? The formula for ratio says that you take the focal length of the telescope, you divide it by the aperture of the optical element, and you get your ratio. In this case, we taken the 200 over 10, and it gives the result is 20. The focal ratio in this system is 20. We use the lowercase f letter to designate that means that number 20 means focal ratio. All right. So you see it now. Any photographers here? All right. So you know all about f-stops in your camera, right? That does bring up an interesting thing to think about. Okay, so you have a lens in your camera, right? I mean, that lens has been made. It's solid. You're not going to be able to change the shape. So how can I change my ratio in my camera if it's an adjustable type camera? By the aperture. As you turn that ring that shows you different what they call f-stops in photography, you are actually operating an iris that is opening or closing. So it's almost like making the lens small, changing the aperture. And that's how you can get different f-stops or focal ratios with your camera. Usually either fancier cameras, okay? I'm still in the 35 millimeter film cameras. I haven't gone into the new digital cameras, but I understand the good ones that you can still change the f ratio. A lot of them have become automatic, though. I notice there's a lot of automatic cameras, but I'm sure that when you start getting up there on a very fine camera, that a lot of things are still adjustable. Okay. The eyepiece, as I said, is nothing more than a very sophisticated magnifier. Here's a diagram of an eyepiece. This particular one has 4 different elements in it, the 4 different lenses. The optician that designs the eyepiece has a specific purpose in mind, okay? And that's why he wants that eyepiece to deliver a certain effect or a certain image, and that's what goes into his design. In the old days, if you notice, it says Plossel here. If you can read there, it says Plossel. In the old days, they used to name the eyepieces after the optician who designed it. Those days are gone. Now they got fancy names for eyepieces, but still, again, when I was a kid, there was about 2 or 3 different kinds of eyepieces that I could purchase. You know, that's not the case nowadays. There's quite a variety of eyepieces with many different purposes in mind. Power. That's a question that I get asked all the time. You know, we do public observing sessions every Friday night at the observatory at Hemlock Crossing. It has to be clear, needless to say. And everybody's always asking, oh, how much power? How much power you got in this telescope? Well, power, or it's another word for magnification, although we do use the word power, once again, is a mathematical calculation. Okay. In theory, I can get any power that I want out of my telescope by just putting whatever eyepiece is going to give me that power. Okay. Now, having said that, we tend to work on the lowest power that we possibly can. You may think that we want to get as much magnification as possible, but no. We use the lower power that will deliver what we try or accomplish what we're trying to see. Why? Well, you guys, again, are closer to my age, so you know all about film. Cameras that use film. Kids don't know film. What do you mean film? You mean a motion picture? No. Photographic film. You remember that you could take a negative and go to the local lab and could get an enlargement. But there was always a limit as to how big a print you could make, right? Because as you enlarge the negative, the image from the negative, you start losing resolution. You no longer have nice, crisp edges. They're fuzzy. You start losing detail. You start losing contrast between dark and light, okay? And the same thing with with magnification. You can magnify the living daylights out of an image, but it's going to be a terrible image. So therefore, we go the other way. I'll use as low power as I possibly can and still get to see whatever it is that I'm trying to do or measure. So again, I get this question all the time. Or also, how far can you see? Well, oh, Jose, can you see? No, it's just our things to explain to the public. But so how do we figure out power? Well, once again, here we have an eyepiece. Gives us an example. This eyepiece has a focal length of 200 millimeters. Now, I have to say that we have still not resolved this thing of inches and millimeters. We're still mixing them up, at least in astronomy. It's improving because a lot of the optical elements these days really come from overseas. And most of the folks took care of the metric problem some time ago. But you still see some things shown in inches. Okay. But eyepieces mostly are all labeled and measured in millimeters. This lens has a focal length of 2,000 millimeters. That's not an unusual focal length for a telescope mirror. Okay. The formula is simple. Power is equal to the focal length of the objective, meaning the lens or mirror, divided by the focal length of the eyepiece. For this example, I take the 2,000 divided by 20, and the answer is 100. Notice that we use a capital letter X after the 100. That stands for power. You see this thing is the 100X, you know that that particular telescope or eyepiece or whatever will deliver, or a combination of the two really, will deliver a magnification of 100 times what I can see with the unaided eye. Now, this same eyepiece, though, used with a different telescope, will yield a different power, right? If the focal length of my lens or mirror was only 1,000 millimeters, you do the math, it would be 1,000 over 20, and that's what I'm getting out of that. That's the magnification I'm getting out of there. So it's a specific eyepiece with a specific telescope will yield a specific power. I said I was just going to talk a little bit about binoculars. And if you have any binoculars, you're going to have somewhere on the binocular, you're going to see numbers like this or a statement like that. You know, they're stamped usually on the front, but it can be almost anywhere. So what does that mean? Well, 7x. We said that the capital letter X was used to define power or magnification. This binocular will magnify 7 times what you can see with the unaided eye. And there's a comma and then 35 millimeters. The second number, and sometimes I don't put the millimeters or even the X. They just say like 7 by 7-35 or something like that. That stands for the aperture, the diameter of the lenses, the big lenses in the front of the binocular. So if you were to see a pair of binoculars, this is an 8 by 50. Okay, then I know I get a magnification of 8 times, and those lenses in the front are 50 millimeters in diameter. As those lenses get bigger, guess what? The binoculars are going to get heavier, right? Or if you get something that has like a magnification of 10, I'll be honest with you, you're never going to be able to hold here with your hands and see something well, because the slightest movement, your breathing is going to move those binoculars. And at that point, you really need something to support the binoculars for you. Okay? Otherwise, you're going to get tired real soon, and you're going to be shaking all over the place. The second statement says wide field, 11 degrees. And I'm going to talk about field of view in just a second, but it is, when you look into that telescope, what is the apparent effect that you get of how wide an area are you looking at. That is referred to as your field of view. In this particular binoculars, it's about 11 degrees. 11 degrees is something about like that. Wide angle, this starts getting to a bigger, 20, 25, okay? Or very narrow, they get down to 6, but then that field is really small, what you're looking at. Why have different fields? Well, for different applications, okay? If you're trying to detect, back in World War II, a ship out in the distance, then they went to something narrow because you don't want to be distracted by light from other sources. You were looking for that particular object in the sky. Same thing with eyepieces. For certain things, certain observations that I'm trying to make, I want a really small field. There's something called an occultation. Occultation is the passage of one object in front of the other one. For example, the moon in front of stars. Right? And as you're looking at this thing, the moon, you see the star, and the moon is slowly catching on it. And it's right there on the edge. And then it's like somebody turned the star off. Why? Because there's no atmosphere on the moon to disperse the light. So it's the moment it happens, that star is gone. Okay. And that's the type of observation that we make. It used to be a Navy program when they were trying to improve their navigational charts back in the old days before GPS and all that, when they were out at sea with a sextant and so forth. Nowadays, we do it because we're improving the position of the stars on our charts. They're not as perfect as we thought they were. So we use that information for that. But for that kind of observation, I want a very small field. I don't want the moonlight to distract me or prevent me from seeing this tiny little star that could be very faint. So again, different eyepieces will allow you to do different things. By the way, that timing of that disappearance has to be at least down to 1/100th of a second. It has to be at least that accurate. Which means that I have to, especially on a cold Michigan night, keep testing my personal reaction. How long it takes me from the time that I see it disappear for my finger to stop my stopwatch. And as you get cold, guess what? Your reaction time slows down. So you have to keep testing yourself to make sure that, because we're talking at such a precise measurement of time. And just a sidebar, some of the research that we do. The field of view, that's what so it's the apparent area that you can see through the telescope or binoculars, okay? This is an interesting diagram. Can you tell me, is the size of the building the same? The building with all the windows, the same on both views that you see there? It is. But what's different about it, the images? I'm sure I can see a lot more than the building in the one on the left, right? Versus the one on the right. Yet, both views are using a 1-inch focal length, or let's say 25mm focal length eyepiece. So that means magnification and so forth will be the same. So what is different about these eyepieces? Well, if you read, you'll see that this one has a 50-degree field of view, while this one only has a 35. So when that eyepiece, those eyepieces are made, the lenses are designed to, again, deliver that field of view. So if what I was talking about before about seeing more or less of the moon, etc., is the example. Magnification is the same because they're both 1-inch eyepiece being used by the same telescope. It's just that the field that I see when I look through the telescope differs from one to the other, depending on what kind of eyepiece I use. I want a wide field eyepiece, I'm going to see more, or a narrow field eyepiece, so I can see a smaller area. Let's say I want to look at a galaxy. I probably need to go to a wide field, especially if they're close to a galaxy like Andromeda. The Andromeda galaxy, right? The only galaxy that we can see naked eye, not in the polluted skies of Holland and Grand Haven and all that, but if you get out to a dark sky, you can actually see the Andromeda galaxy without a telescope or binoculars. Yeah. It's a big area, okay? And therefore, I want an eyepiece that gives me a wide field so I can see all of it. Unless I want to observe something in the nucleus, in the center of the galaxy, then I can go to a narrow field. Again, get rid of all the light from the galaxy. I only want to see this particular part. I'll go to a narrow field eyepiece to do that. I know it's maybe a hard concept to grasp about this field of view, but there are reasons for having wanted to see a lot or just wanted to see a little bit. In some of the old eyepieces, when you look through it, was like looking through a little pinhole. And then in some of these modern eyepieces I have an eyepiece that has the field of view of 100 degrees. It's like sticking your head out of the porthole of a cruise ship or something. Wow, there's the universe in front of me. Yes, sir.
Is that
One second, please, so that the folks online. Yeah.
is that limited by the is that limited by the f-stop by the field of the objective versus the focal length?
No, it's all controlled by the design of the eyepiece itself. Needless to say, if I'm using a 5-inch telescope or a 10-inch telescope, yeah, that's going to make a difference in the amount of light that I'm getting. But the actual field of view is due to the design of the eyepiece. Like I said before, the bigger the telescope, the more light you get, the more detail you're going to see. That's kind of a pretty basic principle. And that's why we have gigantic telescopes these days. Just a rule of thumb that usually the higher the magnification that you're using, the smaller the field you're going to see. Okay. To give you an idea, if you were to put, kind of hard to do, I know, but put your fingers, the thumbs and the index together, you get a teeny tiny hole there, and you hold it at arm's length if you can. That is the area of the sky you're seeing when you look through a telescope. Teeny tiny space, right? Very small space. So you can see that why we use wide field telescopes and why we use magnification. The secondary, we talked about it in the case of a reflecting telescope or a cathodioptric telescope. Anyhow, is that is another mirror, or it could be even more than one mirror sometimes to send the light somewhere. In the big telescopes, they have all kinds of mirror systems to take maybe the light of the telescope instead of right to an eyepiece. Although I'll be honest with you, nowadays on those big telescopes, in the big observatories, nobody looks through an eyepiece anymore. They're all sitting in a comfortable, warm office, looking at monitors, drinking coffee. The days of suffering at the eyepiece, freezing while you're trying to guide a photograph are gone. But to me, the romance is gone. To me, there's nothing like looking through an eyepiece and saying, God, that is the planet Saturn I'm looking at. The way it appeared X number of hours ago, right? Remember, telescopes are time machines. We're always looking into the past. The star that I'm looking at now may not be there anymore. But I won't find out about it for maybe 100 years. And once again, there's a little diagram showing you the little secondary flat mirror. Light comes here, here's the mirror, gets sent here, and then up onto the eyepiece. Little device there is called a spider. It looks like a spider. It is mounted in the front of the scope to support the secondary mirror. It's got to be supported somehow. And it has all kinds of screws that you can adjust because you have to align this thing perfectly, right? Otherwise, the light is not going to go through the hole in the tube, it's going to go off to the side. So, but there are many designs of spiders. There's some of them only have one single vein, some of them have multiple, some of them I try using circles. Everybody has a different idea of how, how it should work and how to minimize the blockage of light and so forth. Eyepiece holder. So now you got this eyepiece, what are you going to do with it? Well, you have something like this. So this device is holds the eyepiece in place. If the eyepiece goes into that hole in the top here, and it's held in place with a thumb screw. Of course, that holder has to be placed in the exact place on the tube, right? So it's in line with that cone of light coming up. Keep pushing the wrong button. This knob here is strictly for focusing. You know, my eyes are different than yours and than his. So I look through the telescope, I focus the image, and I say, hey, take a look. And you go, oh, it's kind of fuzzy. Oh, that's right. You got to tweak it for your own eye. That's what that knob allows you to do. Some of the fanciest one have a high speed and a low speed focuser when you're really trying to nail it, you know. And some of them, like this one, has that once you have found that position, if you're observing by yourself, you can lock it in place with another thumb screw. Some of them now are electric. You push the little button. Because why? Because you turn the knob and you're moving the scope. Okay. Remember, any movement in your body, breathing and all that, the moment you touch the telescope, you're transferring that motion to the telescope. So they have come up with electric ones. I'm not really too crazy about them, but anyway.
So you're focusing it, glasses on?
Ah, good question. You
Just
repeat it?
repeat the question, please.
Surely. The question was, when you're looking through a telescope, can you keep your glasses on? The answer, let me start from the back end. The telescope can correct for like people who are farsighted and nearsighted up to a certain point. So by focusing the telescope, you don't need your glasses, you can correct for that. Now, if you have astigma, the telescope cannot correct for that. Your glasses have to be special, you know. The problem with glasses is some of the eyepieces, okay, when the cone of light comes out of that eyepiece, it can be very close to the eyepiece or a little bit further out. We call that the eye relief. How close do I have to get to the eyepiece? Oh, here's an eyepiece. How close do I have to get to it to see my image? Yeah. And again, different eyepieces have very low eye relief, and some of them have a better eye relief. And that's the problem with glass users, that they cannot get close enough sometimes because the glasses get in the way. There was a company that was that advertised manufacturing an adapter for your eyepiece to correct if you had astigma. I haven't seen their advertisement in a long time. Apparently, they didn't sell a lot of those. But again, yeah, you can correct for most near side or far side by focusing. But the problem with the eye relief is a problem. And I usually try to use, when I do public things, eyepieces that have a good eye relief so that if somebody needs to keep their glasses on, they're not going to run into that problem. And I tell everybody, says, try with your glasses, try without your glasses and see, you know, what's best. If you can do it with your glasses, great. One less lens in the way, right? By the way, every time we put light through a lens or reflect it from a mirror, you're going to lose 5% of the light because you have scattering. So again, we try to keep the number of elements to a minimum. Have you ever looked through a telescope and things are either upside down or reversed left to right? Well, that's part of the whole bouncing of light and all that. Can we straighten that up? Yeah, you have to add another lens in your system. But I just said, every time you throw in an optical element, you're going to lose some light. So we don't care if the image is up. What's up and down in space anyhow, right? I don't care if it's reversed left to right or, yeah, if you're looking at a chart, say for the moon, you have a picture of the moon and you're trying to find something, you're looking through a telescope, you cannot turn it upside down but don't worry, they make special maps that are printed so that it looks like what it's going to look through the eyepiece of the telescope. So, well, yeah, if everybody says it's upside down, or you know, so the arrow says to move here to move the telescope, but it's going that way. It just it's a matter of just getting used to it and learning about it. After a while, you'll even think about it. Same thing with the eye. How many of you close one eye or cover it to observe through a telescope? So a lot of people do. Closing the eye, after a while, it starts getting, the nerve starts getting tired, and you start, moving your eyes around, all that. After a while, you learn that you completely ignore whatever the eye that is not looking through the eyepiece is seeing. I don't close my eyes. I just throw this image. I taught my brain to say, forget about that one. The important one is this one here that we're looking at. It just takes some practice, like a lot of other things take practice and getting used to it. What I mostly tell, if you need to close your eye, don't close the eye and like that, keep it, just put your hand on it. You want to be relaxed. You don't want to be contorted with your face when you're trying to look through this tiny little hole at the object. How's my time? Am I doing okay? Okay, thank you, sir. The finder scope. So imagine that I got this humongous telescope like the one at Hemlock, weighs about 350 pounds or so, that I'm trying to look at a star and I'm trying to move this thing to aim it. It's impossible. Okay. So what do we have? We have something called a finder scope. A finder scope is nothing more than like the telescopic sights you may have in a rifle. Okay. Same idea. It's a little telescope. It's low power, and I want a nice big field. And guess what? When I look through the eyepiece, there, or there, that's a better light, there's a set of crosshairs. All I have to do is go through a process of lining up the finder scope with the main telescope so that they're both looking at the same thing. Then, when I'm trying to find something in the sky, I'm looking through the finder scope. I got a nice big field. I can move the telescope around. The moment that I center what I'm looking at, I want to look at in the crosshairs, is going to be in the center of view of my telescope. All kinds of fancy ideas for finder scopes. This one here, it makes it look like, I know it's kind of weird, and you look through the back here into that glass there. It makes it look like you are projecting a bullseye in infinity. In reality, you're not projecting anything. That bullseye is being projected on this glass from down here. There's a lens there, it's a light source. But they work pretty good. You don't have to be straining through an eyepiece. You're kind of looking at something bigger, okay? That black thing next to it is just the mounting plate. This plate gets attached to the telescope, and then you can remove that for transportation. All that. And again, those three screws and there's three little screws here. That's why you use to align it with the main telescope. That kind of sight, it's called a reflex sight, was used in the bazookas in World War II. They needed something to aim these bazookas that could take a lot of punishment, because the soldiers are not going to be very careful with this thing when somebody's shooting at them, right? And reflex sights were used in some other devices as well. And we copied the idea and use them in telescopes. Why not? What you're trying to do is aim something. The mount. Okay, as important as all the optics are, as important as how sturdy is the tube, in this case, like this little telescope, this tube that holds all the optical elements in place, the mount is equally important. I can have the fanciest, most expensive scope in the world, put it in a crummy little Walmart tripod, and when I go to use it, everything is shaking all over the place, completely useless. So the mount is extremely important. It has to be sturdy. It's got to be adjustable. You got to be able to do things like move it slowly, have slow motion controls. This type of a mount, and there are many different kinds of mounts, but I'm not going to get, but this is called a German equatorial mount. German because the Germans came up with that quite a while back. What's so special about this mount is that it moves in two axes. This one here is called the polar axis. So the telescope would move like that. And the other one that at 90 degrees to it, this one here, is the declination axis. It would move the telescope up and down. If I align the polar axis to the North Celestial Pole, the star Polaris is not right on the celestial pole, but it's only half a degree away from it. So it's a good starting point for aligning a telescope, okay? But once I get that alignment, I can compensate for the motion of the Earth. Okay, so if you get up in the morning, you all know that things rise on the east, where there is the stars at nighttime, or the moon, or the sun, go across the sky, and it sets in the west, right? What is actually the Earth doing? The Earth is rotating from west to east. We don't feel that motion, right? This thing is not moving. This is solid. Why? Because we are going at the same speed as the Earth is spinning on its axis, right? But the effect that we get is that things rise on the east and set in the west. If I can compensate, if I can move in the opposite direction at the same speed, and if the axis that I'm rotating on is parallel to the axis of the Earth, I can compensate for the motion of the Earth. And that's what telescope drives do. They move the telescope at the super fast rate of 24 hours in one day. Actually, it's not 24. Did you know that it's not 24 hours? The day is only really 23 hours, 56 minutes, and some seconds thrown in. Not quite the 24 hours that we use, but it will be kind of a cookie wash if you have to count for 23 hours and 56 minutes. So anyhow, it's called sidereal time or star time. That's what we call it. But anyway, that's what the telescope drive is doing. It's moving the telescope in the opposite direction at the same rate. And that's how I can track an object all night long if I so desire. The alignment process takes time. The bigger the telescope, the harder it is to get it perfect. Okay. I'll be the first one to admit that I'm not 100% satisfied with our alignment at Hemlock. But I wanted it to sit there for a year, go through a winter. Remember that pedestal is going way down into concrete, way down into below the freeze level, okay? And I feel after a year, things will settle down and then we can make it. I mean, it's just almost perfect, but it's not perfect. That's a close-up of it. This thing here is kind of it's a knob that you can do very slow motion controls when you want to do it manually, okay, not with the drive on, to make little adjustments. The counterweights, because the balance of the telescope on any position has to be just so. You know, the motors that drive these things are not, I mean, they're pretty powerful, but you don't want to strain the drive system. So you balance the scope, make sure everything. And counterweights help you to do that. Okay, so here's a little explanation. Well, I don't know if it's an explanation. Sometimes I think I shouldn't put this slide in here. There are basically two different kinds of mounting. This mounting, I'll give you an example. You ever seen a battleship? They have a turret where the big guns are mounted on. Those guns, the barrels can move like this, up and down, or the whole turret can rotate 360, right? Altitude and azimuth, that's what we call that horizontal 360 degrees. We use that for measurements, so forth. When we combine the two words, we come with the azimuth mount. Okay. I can move the telescope in the two directions to point at anything in the sky. If I want to take a long exposure photograph with one of these, I got to be able to move it on both directions at the simultaneously, which is impossible until the advent of the computer. Now we have drives that work with this setup, and they're continuously moving the scope both in altitude and azimuth. The only problem is that you are not really getting rotation of the field like you do when with a telescope track like this. and you'll get rotation in your image. So astrophotographers don't like them very much. But the polar type, which is, it's not complicated. You take this mount and you put it at an angle. And this shaft here is pointing to Polaris. Now you've got a equatorial mount. Okay. By the way, this angle here from the horizontal is the same as your latitude. So whatever your latitude is, like we're here, around here, we're around 43 degrees, give or take. And then you point at Polaris and you pull a line. I know it may be kind of blurry. It's the type of thing that you have to actually get your hands on and look at it. But mounts are very, very important. Dobsonian telescopes. I got to tell you about this guy because I loved him. I had the honor of knowing him. John Dobson. John Dobson was a professor in astronomy, astrophysics, chemistry, you name it. Brilliant man. Okay. All of a sudden, he decided that that wasn't his life. And you know what he did? He became a monk at a Buddhist monastery. But John loved astronomy and loved kids and teaching kids about astronomy. So John would start making telescopes for the kids. He then came up with that idea of using what now is known as the Dobsonian mount, this altitude azimuth type mount, because they're easy to make. You got a handsaw and a sheet of plywood, you can make one of these, real easy. Of course, John, being John, got so carried away that finally the monk told him, this is not your life. Go back to your telescope and your astronomy. He got kicked out of the monastery. But John became kind of the hero of the amateur telescope makers, and he will be at all the different conventions and gatherings and wrote books, and people just loved him because he was a great guy. Unfortunately for me, we would have conversations and he would get into astrophysics and he would get to a point where I found that, John, I'm sorry, you lost me. I don't understand what you're saying. Because he was that brilliant and he would share everything that he did. And of course, he passed away, but again, quite a guy. John Dobson. And so you can buy Dobsonian telescopes today that are made commercially by quite a few different companies. They're easy, they may not be sophisticated for tracking and all that, but you can pick up the tube, pick up the base, walk in the field anywhere, plop it down, you're ready to go. Some of the fancier telescopes, you go out there with several parts. Now you're trying to put little wing nuts and things. In the middle of the night, you drop it in the grass. You're never going to find it again. So they're very nice telescopes for a lot of things. And again, I don't know why, a close-up of a German equatorial mount, very sophisticated, a lot of machining, and gears and bearings and all that wonderful stuff. And now, today, we have the go-to telescopes. Thanks to the marvels of processors and computers, now you can buy a mount that has a computer built in, that you have a little hand controller where you go, I want to see Jupiter. The telescope will figure out. He may come back and say, dummy, it won't rise in the sky until 2 hours from now. No, it doesn't call you a dummy. Or it'll say, okay, here are the coordinates. What do you want me to do? Well, I want you to go to it. You press the go to button. Zoom, there it is. Now, I'm an old-fashioned astronomer. I learned the sky by laying on my back with a star chart and learning the sky, just like you learn your neighborhood streets, right? So I said, okay, this go-to telescopes, you know what is creating amateur astronomers that do not know the sky because they don't have to know the sky. I want to see the Orion Nebula. I want to see the Andromeda Galaxy. Okay, that's all. Just press a button. It'll go there. That part I don't like. But what it has done is brought more people into the hobby simply because the telescopes now are easy to use. So, you know, it's the balance back and forth. I don't talk them down. I do talk them up. Well, the telescope that we have at Hemlock is a big telescope, and of course it's computer control. And of course it's got the hand paddle. And yeah, I use that more than trying to go through other devices that we have for pointing the telescope, because there takes a lot more time and precision. So that's the latest craze, and they're getting, like anything else, less and less expensive, right? And they look something like that. In this particular model, that's the hand paddle that you can detach, and you sit there and you talk to it like you talk to a computer, right? You go through menus, you know. Okay, I want to see an object. Yeah, that's what I want to see. What kind of object? Solar system. Yeah, solar system. Okay, here's a list of the planets. Which one? Oh, that one. Okay. What do you want me to do? Go to it. Okay. Being computers that go haywire once in a while. I'm having a problem right now with the one at Hemlock. They seem to have a mind of their own sometimes. Any computer guys here? Oh, okay. Well, then you know what I'm talking about, I guess. Or it's user error too. Be the first one to admit that I have pushed the wrong button in the darkness. Somebody even came out with a Dobsonian telescope that has not necessarily the really fancy go-to, but it does, as you move it, it says this is the direction you're pointing at. So that makes life easy too. And you see the control paddle is hanging on the side there. Changes and changes and changes. You see more and more telescopes now being made of the go-to type, simply because people buy them because they're easy to use. You still got to go through some adjustment or some alignment process, but the telescope at Hemlock has a GPS built into it. So once I turn the power on and it goes through some kind of self-test, then it turns on a GPS and it'll go looking for how many satellites can I connect to, and it does. The number of satellites at any given time differs depending on where they are. Once it gets information for every satellite, it knows exactly what time it is, what day of the week it is, and it can triangulate its position. The telescope say, oh, I know where I am on the surface of the Earth right now. Great, what do you want to see? I can find anything you want. So, that's pretty cool. That little telescope, I'm not pushing this brand telescope, but some years ago, somebody came up with this very nice, very portable, very simple telescope. It's small. You're not going to see some fantastic images, needless to say, but we have started a program with libraries. We give them brand new telescopes like this and tell them, here's some ideas of how to manage the program. Well, you do what you want. You manage your program the way you want to. A family is going camping, they can go to the library and check out a telescope and take it with them. Okay. The Herrick Library has the program. We're working with Luther Librarian where I live in Grand Haven, with where the university is. I can never remember the name of the town. Why? Just Grand Valley, Allendale. Thank you. Mental block on Allendale. Anyhow, we're trying to go to different libraries and get the program going. I said, guys, it's another offering that a library can do. And it won't cost you much. Yeah, you'll come out with what kind of container you want to put this in. You need to put in some kind of container. We can give you some ideas, but it's up to you guys to decide how you want to package it. And it's a tabletop. You put it on a picnic table or something, and easy. You loosen the knob up and down. It's a Dobsonian mount, right? It goes around in azimuth and it goes up and down. It's got a little finder scope. The crosshairs, so you're welcome to come and look at it. The mirror is there at the bottom. 3-inch mirror. Okay. So anyhow, and there are a couple of versions of this that are getting a little bit bigger. Okay. But a lot of times I'll recommend that for small children that are just getting started. This is just what it is, 3-inch mirror, blah, blah, blah. Comes with a couple of eyepieces. Most of them are useless, but And I always close with this, solar observing. Don't look at the sun. With your eyes, with binoculars, with telescope, do not. Unless you have the proper equipment, right? If you have the proper filter for the telescope, then you can safely look at the sun. So for the Hemlock telescope, we do have solar filter, a special solar filter for it. And you can safely look at sunspots and so forth with it, especially when you have an operator who knows what he or she is doing, okay? Under those circumstances, yes, you can look at the sun. But not, back in the old days of Kmart, they used to sell this Japanese refracting telescope with a long tube. And it came with a blue filter that you would screw on the bottom of the eyepiece, and they call that a solar filter. And people will come to me with those scopes and I say, take that filter in your hand. Okay, let's see how far away you can throw it away. Don't ever use that. All that light that's being concentrated, all that heat is being concentrated on that stupid little filter made out of glass that can crack. And the moment it cracks, goodbye eye. Your retina will be fried, okay? So you have to be careful with what you're going to observe with. I know they sell the solar glasses for eclipses, right? They can be gotten very popular. Because you have to very carefully inspect it before you use it. Make sure there are no scratches in that film. It's only a plastic film right in front. So again, be careful. We always inspect our filters completely before we use them. If there's any kind of scratch or anything, that's the end of that filter. You throw it away. You just got to be careful. You have to know what you're doing. We only get 2 of these. I don't know. We got to take care of them. So commercially made filters or not, take care of your eyes. Finally, questions. I know I've thrown an awful lot of stuff at you guys, but hopefully it'll help you to read catalogs. Sir.
Hold on a second.
Yeah.
That everyone can hear you. Oh, sure. Thank you.
Someone told me one time to be careful looking at the moon with telescope. Do you have to worry about that?
Well, it's very uncomfortable when you have a very bright moon, like close to full. Well, and I have filters that I put in the eyepiece just for moon filters. Yeah, after, up to about first quarter is okay, but then the further on, the more the moon that gets illuminated, it can get pretty bright. You look, and it's funny because people are looking through the eyepiece and I can see the moonlight illuminating their face. I go, oh, hold it, it's time to get a filter in there just to make it comfortable. But no, it wouldn't really hurt your eye. It's just that it's like the headlight, look under the headlights. The deer looking at the headlights, all that light goes.
I may be getting ahead of next week.
That's
but
okay.
What kind of telescopes do you personally have in your possession?
I have reflecting telescopes. I got my very first commercial telescope that I purchased as a teenager. I still have it. And I will tell you next week, so you come back, I got to keep you in some suspense. Why we're getting to the bigger and bigger telescopes, why that works with all reflectors and all that. But yeah, I like reflecting telescopes because you could get the most seeing for your buck. Yeah. And in my days, in my youth, the refracting telescope, the ones that use lens, highly expensive because of the cost of manufacturing. I have ground mirrors for telescopes. Okay. It can be done. It's an awful lot of work. And it's messy, but it can be done. A lot of amateurs in the old days used to make their own mirrors because they couldn't afford the commercially made mirrors. Nowadays, you can buy a mirror already made, all ready to go, cheaper than you can buy all the kit and all the chemicals that you need to grind your own mirror and spend about 300 hours, 400 hours grinding away by hand.
Tell us a bit more about that. Your youth, tell us a bit about how you went from assembling one telescope, moving to the next level of complexity, how
Yeah.
much it might have cost at the time, and relate that to today. If someone wants to buy a decent amateur telescope, where to buy it and how much might it cost?
Okay. First telescope making. I started making telescopes by buying the lenses at the back of the comic book for $2, and then getting cardboard tubes from the local fabric store, and jerry rigging everything and making my own eyepieces and making a telescope that had a lousy image, but it was my telescope, and I made it. And then you go from there. Yes, I got more sophisticated, learn more, and the more you learn, the better you can be, and the more better tools that you have, the more things you can make. I did a lot of astronomy on my own until the time that we moved to the United States. I'm from Cuba, in case you haven't picked my accent by now. New York City, okay. I lived there for quite some time. But it wasn't until I moved to Milwaukee, Wisconsin, that I came across my first organization, okay, an association, astronomical association. And I got involved with them. I eventually became president and this and that. A very old member of the society passed away and left $60,000 to the organization. Wow, that was a lot of money. And that is what triggered us to build our own telescope, 26 inches in diameter. We partially ground the telescope at the mirror. We went as far as we could with what we had, and then we sent it to a lab to finish it. We built the building itself. We built the dome, all the electrical work, all the engineering work, and we built a 26-inch telescope that you would find on an observer. I mean, this is a research instrument. That was my first biggie. Before that, 12-inch telescopes, 6-inch telescopes. Yeah, I built a lot of different telescopes, or would refurbish old telescopes for people. I still do that today, by the way. We will accept any telescope you don't want. We'll refurbish, finish it, and then find a child who really is turned into astronomy. Here's your scope. Yes.
And related to today, for people who wish to buy a telescope,
Oh, okay.
the variety available, the cost range.
Okay, there's only one place that I know that actually a store you can walk into and buy a telescope, limited supply, or not supply, but models. Writers Hobby Shop on 28th Street in Grand Rapids.
Apparently. Oh, yeah. Well, here you go. Oh,
Hello?
Right there.
They got all kinds of stuff for model airplanes and railroads and all that, but they do sell some. Otherwise, you got to go online. Okay. What to buy? That's a difficult thing. What is the age of the person who's going to use it? What is their level of knowledge in astronomy? You can buy a really fancy telescope and spend $5,000, and then you don't know what to do with the silly thing, because you read the book and it's Chinese. That's why I should concern. Okay. All these alignments and then. For a child, I wouldn't go, depending on their age and their interest. Oh yeah, I want a telescope. They use it twice and it goes in the closet, right? You know how many closet telescopes we get, or they see one in a rummage sale for sale. Oh, only $10. It goes home. How do you use this thing? The manual is gone, of course, and eventually it goes back in the closet, and then it goes in the next rummage sale. And these things you go around and around and around. I say read, find yourself books that talk about astronomy and telescopes, and get a little bit of knowledge behind yourself before you're going to put down big bucks. Okay. Or buy something like this, $65, something like that, and fool around with it. And then you know where you want to go from there.
We have a question online.
Yeah. So I'm going to rephrase it a little
Yeah.
here, but so then would you recommend, a lot of mid-range telescopes these days have the ability to use apps from your phone to help locate the stars and track, and even have red dot finders?
Well, you can do that again if you're good at using apps with your phone and understanding that you're going to have to align the telescope. Even though you're using the app, first you got to align it, and do you understand what they mean by alignment? You can read about it, and see, okay, I get that or no, I don't get that, you know. If you don't get that, you can come to us. We'll try to help you out, you know.
But you would say that those apps are accurate.
Oh, most of them are. They're, yeah. Well, what about the apps that shows you the constellations? Maybe you guys using your phone? I know we're running out of time, but funny story. When they first came out, one of my friends came to me and go, Frank, look at this fantastic thing I found. You know, we can have the whole constellation. And he just has me the phone and I'm looking at it like this. And I go, God, I don't recognize a single constellation here. Then I realized I'm looking at the southern hemisphere. The kind of stuff you see in Australia, not here in the good old USA. Oh, there it is. And it's simple things like that I come across people saying, I cannot, you know. I had a teacher who got one of these, write to me and says, I cannot figure out, when we look through the telescope, we see in the front, but when we look through this, we see the back. I go, man, you have this thing turned around. Put the big part in the front and the little part in the That's the kind of things that you come across. I mean, it's not that people are stupid, it's just that it's a completely foreign thing to them. What the heck is that? How do I? And nobody reads manuals these days. Yes, ma'am.
I just want to make a comment. My excitement with astronomy came as a child here in Holland, Michigan,
Yeah.
where I think it was through my mother being a scout, Cub Scout leader or whatever, for my brother,
Yeah.
3 years older than I, and they brought one of those things that you can see it on the ceiling. And we
Right.
got to see it on the
A little
ceiling.
projector
And-
thing?
Yes, and it was so fascinating because it wasn't like you had to sit outside.
No,
and fig-
yeah.
And you had somebody that was explaining to.
They got
And it
little
was just so
homemade
fascinating.
planetariums that you can put in your living room. And I got one that is considered now a vintage antique and it's worth a lot of money that I bought a long time ago.
One
That's
more.
a good way to learn your sky, by the way. You know.
I had the privilege of being in a dark sky area last year in Alberta. For those of us who don't know, tell us what it is, how they came about, why they're important, these dark sky areas.
Unfortunately, with progress comes some problems, right? Pollution is a big problem in many different things. Light pollution is a very big problem for us. I arrived in Grand Haven in 2007, and I have noticed the tremendous decline on the quality of our sky in that period of time. I could see the Andromeda Galaxy naked eye from Hemlock Crossing when I first started using the park. Yeah, I was a little younger, but you know, I just had cataract surgery, so I got perfect eyeballs right now. But the light pollution because of the growth, you know, more houses means more light. There's an awful lot of horrible, useless, wasteful lighting out there that add to the light pollution. Now, the light pollution takes away the night sky from us. Somebody say, oh, big deal, right? But we have access to the planetarium at the Macatawa Bay Middle School. A lot of people don't know there's a planetarium inside that school. It's not being used by the school anymore since their astronomy teacher retired years ago. We use it as to hold our meetings. We have access to it. And we're the ones who fix it and keep it running because it's a shame to leave this thing going. But anyhow, so we'll do planetarium shows as long as we can arrange it with the school. And every time I do things for kids, I set up the machine. I say, okay, it's late afternoon, it's getting dark, it starts getting dark, the sun is setting in the west. And the stars come out and say, okay, you're looking at the sky the way it will look tonight in Holland and in Grand Haven. I tell you what, I'm gonna take you to the Upper Peninsula. And I change the controls and the kids go, oh, they have never seen that. They had never seen a true night sky that is lit up. I mean, starlight, you can actually illuminate things with it. And that is it's a shame, I think, that we don't have that anymore. So the International Dark Sky Association is an association to do what, do you think? Trying to reclaim our night sky. And they have, well, they certify as a dark sky park. There's one by Traverse City, nearby there. There's one on the east side of the state. not too far. There's an old Air Force base. I can never remember the name of it, but anyhow, there's another one there. There throughout the world, you'll find them. And that's the whole idea. They got to have certain standards for lighting and so on and so forth. We try to save as much of the sky as we can. But if you look at a picture, like taken from the space station of the Great Lakes, they all lit up like a Christmas tree at night. At one time, we used to illuminate billboards from the top down. Somewhere along the lines, the industry got to say, no, we want to put them from the bottom up because it's easier for us to get to the lights. If you ever look at any billboard on a foggy night, I bet you that at least 1/3 of the light coming from those fixtures never hits the billboard. It goes right up into the sky.
When I went to school,
Mhm.
I went to school in Tucson, Arizona, and about, I think it's 50 miles away or so was Kip Peak National Observatory, this is now in the early 70s. And at the time, it was the largest collection of optical telescopes in the world. They had the light problem back then. We're like, again, talking 71, 69, those timeframes. The city put, they changed all their street lights
Yep.
and put metal rims around them to keep the light from going up into the sky.
Light shields. yeah.
So, yeah, so that, and they did a number of other things, but I remember reading in the newspaper and so forth, and through my classes, I got involved with Kip Peak, and anyhow, that was a big issue, and they made a huge difference.
Yes, it did.
Probably different now, but
Tucson has been very good to working with Kip Peak. For Kip Peak, it's a national observatory. They have a little push, I guess. But they have been very good about it. But I bet it had been a very long time since I have been in Tucson from the previous time when I had been at Kip Peak. I could not believe the growth in Tucson. There are subdivisions all over Kingdom Come. They're beginning to build houses up the mountains. It's amazing, you know. And the light again has been a problem to Kip Peak, and they still keep trying to. Even Grand Haven. The thing that ticks me off is that we have light ordinances in Grand Haven. They just simply don't enforce them. There's a house that was just built that I'm going to go to the town and say, who the heck inspected this house when it was built? Because you don't meet your guidelines. You know, it's a simple matter as getting the right light fixture will take care of a lot of the problem. There are nowadays good light fixtures that put the light where you want it, down on the ground. There's no use putting light up there or way up there. If you drive to certain street lights, you're blinded because the light bulb is visible. You don't want it. You want a fully enclosed fixture that the light source is inside and the reflector is putting the light where you want it. You know. Save energy in the long run. I mean, that's another way to look at it. Light pollution is a problem for wildlife. You know, I mean, there's other problems besides us to want to see the dark sky associated with poor lighting. Take a look at your outdoor lights at your house. Maybe you can improve them a little bit. You know.
Any other questions, comments? If not,
yeah. I mean, I love it anywhere I can go. I've been in New Mexico. I've been in Arizona. My work used to take me to the Hopi Indian Reservation in Arizona. Wonderful people. I love the Hopis, made good friends there, and I was allowed to go to Second Mesa, which is not, white folks are not allowed in there. Anytime Frank went to, Frank, you go up, you observe anything anymore. I went there to observe Kamihali when he came, and it was fantastic. Yeah.
anything else? If not, I invite you to come back next week. Frank will talk about the early design and evolution of the telescope. He'll drop a few names that you know and maybe some that you don't know. Thank you very much for joining us.